Right. Okay. Okay, we'll start. Can you confirm whether my audio is clear and about the video quality? I will also check from my end. Okay. It's fine, right? Okay. Right. Good evening. Clear. Okay, thanks. Good evening. We'll start. I think it is shared for all the channels. Yeah. Yes. Yeah, I have already shared the live for all channels, right? You also can share if there's anyone who wishes to join, who need to join, any friend, if needed, you can share. Right, this is a free YouTube live session that is happening as this discussion, no? So that is totally fine. All right. Right. So today we are going to have the third day of the S2A discussions. Right. We are going to have the third day of S2A discussions. We started 2 weeks back. Right. And today my plan is to start the questions from vectors and equilibrium, vectors and force equilibrium. Right. So we'll be touching that area today. Right. If you haven't watched the previous two S2A discussions, right? If you didn't join the live session, and if you haven't watched the previous two recordings of the S2A discussions, what you can do is you can watch them as well, right? So there we have completed linear motion parts, right? Linear motion parts, and today we'll be moving ahead with vectors and equilibrium of forces. Okay, right. Then without further ado, we'll start, right? We'll start. Let me share my screen. Okay, my screen is visible, right, students? Okay. Right. Then let's start. So if you haven't downloaded the questions yet, I have pinned a message in the live chat, or else you can go to the video description, right? Video description, and you can get it from there as well, right? If you haven't downloaded the questions yet. Okay, let's start. Okay, then first one. Which of the following diagrams it should be shows addition of two vectors 8 newtons and 6 newtons, right? So for this, the basic theory part we know, the basic theory part behind this that we know is vector triangular law. Vector triangular law, right? So what vector triangular law says is, if we can represent two vectors by two adjacent sides of a triangle like this. Now as an example, say this is ABC. So if we can represent these two vectors using these two sides of the triangle as vector AB and vector BC, the resultant is given by the vector between, one more second, resultant is given by the vector between the starting point and the end point, like this. Resultant is given by the vector between starting point and the end point, right? Now mathematically, if we express this, this is like vector AB plus vector BC equals vector AC. right? Vector AC is the resultant. Vector AC is the resultant, right? Then there are like few laws, few rules when we are using triangular law. One is these arrowheads. Look at here, look at the screen. These arrowheads should be in line. These arrowheads should be in line when you are applying vector triangular law. Arrowheads should be in line, which means they should be in the same cyclical direction, right? Not the same direction, same cyclical direction. They should be in the same cyclical direction like this. Arrowhead should be in line. One thing, right? And this is applicable only for two vectors. This is applicable only for two vectors. Right now, if we represent 8 and 6, 8 and 6 should be represented by same cyclical directions. So one is wrong, right? In 2, 8 and 6 is there. But for 8 and 6, the resultant is not going to be 14 because there is a vector addition, right? Vector addition. See what is happening? If you add 8 and 6, 8 and 6, 8 and 6, wait. If you add 8 and 6, if you add 8 and 6 like this, right? This is going to be right angle triangle, no? Then this is root 8 squared plus 6 squared. So that will be 10. That will be 10. So therefore, addition should be 10. Addition is 10. 8 and 6 should be in the same direction. And always the resultant is coming from the starting point to the end point, right? Starting point to the end point. So answer 3 is correct. In fourth one, that is not from the start to the end. 4 is wrong, right? 2 is wrong, 14. In this one, vectors are also wrong, right? Answer 3. A question from vector triangular law. A question from vector triangular law. Vector triangular law, right? Hope it's clear. So if anything, all of you can put your questions, doubts if you have anything to the live chat box, right? If there's anything. All right, let's move on. Second one, which of the following sets of forces never produces a zero resultant? Right. Now here, for these type of questions, this is a popular type. This is a popular type. For these type of questions, we are using something like this. We are using something like this. Now, if I link this with the vector triangle you learned just before, right? Vector triangle you learned just before, right? Say now we have a vector triangle like this, a vector triangle like this, right? As AB, BC and CA. Now in this vector triangle, what is happening is this vector addition, vector AB plus vector BC plus vector CA becomes 0 because resultant vector is the vector between initial point and the end point, right? Resultant vector is the vector between initial point and the end point, right? I can explain this either by using vector triangle or using vector additive law. First, I'll explain using the triangle. Listen, using the triangle, if you add vector AB and vector BC, its resultant is going to be vector AC, no? Its resultant is going to be vector AC. But instead, here I have already given a vector CA. This is a vector CA, no? Here I have already given vector CA. This means vector AC plus vector CA, right? Means vector AC minus vector AC. That gives 0. That gives 0, right? That is one way that you can think of this. Or else we can apply the vector additive law. What is vector additive law? Vector additive law means if you have multiple vectors of same coefficients and same cyclical directions like this, A, B, C, D, E, F, let's say, right? At once, this resultant can be written as vector AF. At once, this resultant can be written as vector AF. Always the resultant is given by the vector between initial and final points. Initial and final points. This is given by the vector between initial and final points, right? Initial and final points. Now in this scenario, there's no distance between initial and final point, no? Because we are starting from A to B, B to C, C to A. Now initial point and final point both is here at A. There's no distance between A and A. So that diagram produces a zero resultant. So this diagram produces a zero resultant. This diagram produces a zero resultant. Then the idea that I'm going to take out from this is The idea that I'm going to take out from this is, if it produces a zero resultant, then we can draw a vector triangle. We can draw a vector triangle if it produces a zero resultant for three vectors. For three vectors, you can draw a vector triangle as it is coming back to the initial point, right? So if we are drawing a triangle, we know this. We know this from O levels, right? Say these sides of a triangle. See, say these sides of a triangle are ABC, right? Addition of any two sides should be, if we are to draw a triangle, if we are to draw a triangle from simple geometry, we know addition of any two sides of the triangle should be greater than the third side of the triangle, right? Addition of any two sides of the lengths of the triangle should be greater than the third side of the triangle for any two, for any two, for any two. So let's apply this theory here. 5, 5, 5. 5, 5 means 5 plus 5 is 10. That is greater than the third side. So triangle can be drawn. See how I'm going to eliminate these answers. Here a triangle can be drawn. And second one, 5, 5 and 10. No triangle can be drawn, but we know when 5, 5 acts to one direction and 10 acts to the other direction, it produces 0. Like this. If these 2 5s act in this direction and this 10 acts in this direction, it produces 0, 1. It is also correct. Third one, 5, 10, 10. 5 plus 10 is 50, greater than 10. So we can draw a triangle. And this one, 10, 10, 20, same as the second one. That is not a triangle, but in the same direction, it acts opposite and produces 0. In fifth one, 5 plus 10 is 15. That is less than 20, which means you can't draw a triangle at all. You can't draw a triangle, which means it never produces a 0 resultant. So answer is 5. Got it? See how these theories are used. See how these theories are used. Right? Take down if anything. Right? Take down if anything. Let's move on. 3. A child of weight W hangs at rest from the ends of a light inextensible rope, as shown in the figure. If the weight of the spring balance SC is negligible, the reading of the scale is, okay, balance reading. So one more thing you have to know is spring balance reading, reading of a spring balance. See, reading of a spring balance is equal to tension on hook is equal to tension on hook, right? Then as a reading, what we are going to find is tension on that hook. As a reading, what we'll be finding is tension on the hook. See, now if I mark forces here, see, if I mark the forces here, this is W, right? And on this side of the spring balance, there's a T, right? And for the other side also, there will be another T. Since the diagram is too small, it won't be that visible if I mark it. Let me mark this way. One tension here is T, and the other tension on the hand is T, like this. And here T, 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 T. So likewise, this is a force diagram. Now my target is finding T now. To find T, I'm going to use this force frame. See, this force frame here. Right, considering vertical equilibrium. Look at here. Considering vertical equilibrium, vertically upward forces equals vertically downwards. Vertically upwards, we have 2T. T and T, 2T, because this thing cancelled each other. There is an internal force, cancels each other. 2T remains, equals W. Then T equals W over 2. Now check the tension on hook. Tension on hook is this one, no? This one. circling with yellow. This is the tension on hook. So tension on hook is T. Tension on hook equals T. Then T equals WO2, which means reading is WO2. That's a simple calculation if you get the question. That's a simple calculation if you get the question. Right? Take it down. Was there anything on the chat that I didn't respond? I didn't see the message. If possible, put again. Right? I was looking at the screen, screen of the pad, writing the question. Take it down. So if I miss anything, put it to the chat again so I can respond. Take it down. Right? Let's move on. 4. The diagram shows a uniform rod resting horizontally on two supports X and Y. The lengths PQ, QR, RS, and ST are equal. Right. So if they are equal, let me label them as L, 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 L. They are equal lengths now. Right. As Y moves from S to D, Y moves from S to D, something like this. As Y moves from S to D, keeping XZ stationary. X. What is XZ? Not XZ, it should be X. Keeping X stationary. The reaction on rod due to X. The reaction on rod due to X. Okay. Now let's mark these reactions first. Reaction here due to X. Let's say Rx. Reaction here due to Y. Let's say Ry. Right? It follows an equilibrium. No, there's no motion. There's no motion for the object. It follows an equilibrium. For a system in equilibrium, we know either sigma F in the sense algebraic summation of forces along any direction should be 0, or else sigma G is algebraic summation of force moments about any point should be 0. Right? Those two are the two things we can do. Right? Those are the two things we can do. So let's assume mass of this rod as M and its weight as mg. Right. Now, what if we check the values of Rx and Ry here? Let me check it here. Right. Let's check values of Rx and Ry here. To find Rx and Ry, first we can consider a vertical equilibrium. See, vertical equilibrium. Vertically upward forces equals vertically downward forces. Upwards we have Rx plus Ry, downwards mg. Right? We will keep it as 1. And then we can write a force moment. Let's write a force moment about Y. Considering the equilibrium. Force moment about Y, because my target is find X. Then in clockwise direction, mg rotates. Mg rotates in clockwise direction. No? Mg rotates in clockwise direction. Force moment is mg times L. Rx rotates in opposite direction. Force moment is Rx into 3L. L cancels. See, Rx equals mg over 3. We have one answer. Rx equals mg over 3. If that is known, if you plug that value here, right? If you plug that value here, Ry should be mg minus mg over 3. No? Then Ry is 2mg over 3. These are the initial values. 2mg over 3 initial values. Right? Now similarly, to check whether it is going to increase or decrease, I'm going to find Rx and Ry again in the second scenario, final scenario. We can find Rx and Ry again in the final scenario. Then at the final scenario, Y is taken to here. Then let's say new value of Y is Ry dash, and new value of X is, let's say new value of X is Rx dash. Right? Now still for this scenario also, this is a final scenario. Still for this scenario also, if you consider vertical equilibrium, see, if you consider vertical equilibrium for this scenario also, Rx dash plus Ry dash equals mg. No, that is same. Then to find one force, right? If you can say this as symmetrically divided and one as mg over 2, right? you can quickly take it down. You can quickly consider it. You can quickly consider it. But if you don't see it, you can go to the force moment like this. Write force moment about x again x. So y, right? We'll write about x. Now, if you write a force moment about x, see what's happening. In clockwise direction, what is rotating? Sorry, anti-clockwise, ry dash. Total distance is 4L, no? Perpendicular distance. Clockwise direction, mg, and distance is 2L. L to L cancels, 2 to 4 cancels 2. See, ry dash equals mg over 2. If there is mg over 2, now from here you can get rx dash should also be mg over 2. No? Okay, now see what has happened. Look at the screen. See what has happened. Now rx was initially mg over 3. And second scenario, it has been mg over 2. mg over 3, mg over 2. mg over 3 is a lesser value compared to mg over 2. No? Then this has been increased. Right? And for ry, it goes 2 mg over 3. And now there is mg over 2. So this has been decreased. Because 2 mg over 3 is 0.6 something. Right? mg over 2 is 0.5, no? So it is decreased. Now we are done. Then rx is increased. What about rx? Rx increases. And that due to y also increases. No, y decreases. Increases and that due to y decreases. 2, no? Answer 2. See, that's a good question. Right? Take down if anything. I just found the values of rx and ry in these two scenarios, and compared. Right? So if any questions, you can raise. Let's move on. 5. Two spring scales of negligible mass are connected together at 10 kilogram mass is hung as shown in the figure. Which of the following statements is true? Right. Each scale, okay. About scale readings again. About spring balance readings. Reading of a spring balance is tension that I explained before. So this is 100 newtons. And let's say this tension is T, like this. Right? This is how tensions are. Right? Right. Then to find tension, what if we consider the vertical equilibrium of this one? It's done, no? See? By vertical equilibrium, T equals 100 newtons, which means T equals 10 kilograms. Right? Now, if T equals 10 kilograms, tension on the first balance is also T. Tension on the second balance is also T, because I mark them at once. The reason is, now if you consider a system like this also, first spring balance also, it should be in equilibrium, no? If there is in equilibrium, total downward force on the spring balance should be equal to total upward force on the spring balance. That's why it should be T. Right? For sure it should be T. Right? For sure we can say it is T. Got it? So therefore they are equal. Then each scale will read 10 kg. Right? Each scale will read 10 kg. That's an easy one. Right? 6. A system of coplanar forces acts on a rigid body. If the resultant of moments of the forces about a certain point of the body is 0, consider the following statements. Moments about a certain point is 0. Right? Moments about a certain point is 0. Moments about a certain point on the body is 0. A certain point. Right? So if a system is in equilibrium, right, sigma f should be 0 along any direction. along any direction, right? And sigma g should also be 0, right? Around any point, around any point, not only one point, around any point. Then statement A, the resultant of the moments of forces about any point, any other point on the body always 0. Wrong. We can't say having one moment 0, that you can't say, we can't say that all other points are going to be 0. No, that we can't say. The body must be in equilibrium. No, we can't say, because if there is an equilibrium, force moment about any point should be 0, not only one point, right? Force moments about any point should be 0. See, the resultant force acting on the body must be 0. Can't say, because having just one force moment 0 doesn't mean that forces are going to be 0. We can't say, right? All are false. Then all ABC are false. Answer what? All ABC are false, right? All ABC are false. Next. A man of weight 500 newtons standing on a platform supported by two light strings passing over a light smooth pulley. Pulleys A and B supports himself by pulling the string as shown in the figure. If the weight of the platform is 1000 newtons, the force exerted by the man on the string to keep the platform. By the man on the string. Right. Then if we mark the weights here, this is 500 newtons, and the platform 1000 newtons, right? And other forces are, this is a single string, no? Let's say this is T, and this force is also T. Now, if you consider the equilibrium of this one, look at here, if you consider the equilibrium of this light pulley, right? Already it has a downward 2D. Then to counterbalance it, there should be an upward 2D like this. Then this becomes 2T. This tension also becomes 2T. And all the way up to here, the tension becomes 2T. Right? Now, force on the string by the person is T now. Now my target is finding T. So let's find out T. To find out T, what if I consider a force frame like this? Something like this. Considering the vertical equilibrium of this force frame. See, considering the vertical equilibrium of this force frame. Upwards we have all internal forces cancel each other, right? All internal forces cancel each other. Then here a 2T remains, right? Here a 2T remains, and here a T remains. 2T and T, 3T upwards all together. 3T acting upwards all together, right? 3T of 4T. Oh, wait. 2T here, 2T, 4T. 40 acts upwards altogether. From here, there's 2D. Let me circle the ones coming. This 2D remains, and this 2D remains, right? Then 40 equals downwards 1000 plus 500. Then 40 equals 1500. So T equals 375 newtons. 375, answer 5. 375, answer 5. Right? 8. This is again very much similar to the previous question I discussed. Which of the following group of forces acting on a body cannot have a 0 resultant? Right. Then think about the triangle. Whether you can draw a triangle or not. Right? 2, 2, 2 means we can draw a triangle. 2, 3, 5 greater than 4, you can draw a triangle. 1, 2, 3 greater than 2, you can draw a triangle. 1, 1, 2, we can't draw a triangle, but when they act opposite, it produces a 0 resultant. That is also correct. Here 1 plus 2 is 3 less than 4, so you can't draw a triangle, which means it never produces a 0 resultant. Right? So I explained the same in question 203, right? That's why I explained this quickly. We explained the same in detail, comprehensively in question 203. Right? Let's move on. 9. The diagram shows two boys pulling a bucket of water from a well. Okay. Which of the following graphs correctly represents the variation of the tension T in the string with angle theta? Right. Then let's consider the weight of the bucket as W. Weight of the bucket as W. Now, see what happens if you dissolve these forces into components. If you dissolve these forces into components, see, towards the angle, this is T cos theta. See, towards the angle, this is T cos theta. No? T cos theta. Now, from this one also, another T cos theta is coming. And this is T sin theta. This is also T sin theta. Right? These two are equal and opposite. These two are equal and opposite. So, these two cancels each other. Right? So, therefore, let's consider vertical equilibrium. Vertical equilibrium. Vertically upwards, we have 2T cos theta altogether. Downwards, only W. Right? Now, if you are to plot a graph, subject T, then T equals W over 2 cos theta. Right. Isolate the variable, then it is easy to understand. Then this is W over 2, right? 1 over cos theta, no? W over 2, 1 over cos theta. 1 over cos theta. Right? Now, this is going to be my y-axis, right? And this is like 1 over cos x because theta is acting as x here, cos x, and this is a gradient. Whatever it is, a product with this variable is a gradient. Now, since it's a trigonometric variation, kind of critical. Listen, since it's a trigonometric variation, this is not as easy as an algebraic variation, right? You have to have an idea about the variation of cos between 0 and 90, right? If you don't know this variation, I will quickly remind, this is the cos variation between 0 and 90. This is how cos theta varies with theta. Cos 0 is 1, and this is how it goes. That's a sinusoidal variation. Let me use a different color like this. This is how this cos variation goes. This is how the cos variation goes, right? This is at +1. This side is at -1. This side is at -1. Right? Then between 0 and 90, this is what is happening. This is 90, pi over 2. Right? So simply, cos 0 equals 1 and cos 90 equals 0. Right? Cos 0 equals 1 and cos 90 equals 0. Right? The value decreases. The value decreases. No? See what's happening? Now, initially, when theta starts from 0 in the graph, this is a good question. Listen, when theta starts from 0, see, when theta equals 0, see, when theta equals 0, this T should be, see, T should be W over 2, 1 over cos 0. 1 over cos 0. Cos 0 is 1. So T starts at W over 2. No? T starts at W over 2. T starts at W over 2. Right? T starts at W over 2. A value. Right? A distinct value. And when it is reaching 90, see what is happening? When theta equals 90, see what's happening when theta equals 90. See what's happening when theta equals 90. See what's happening when theta equals 90. When theta equals 90, T equals W over 2, 1 over cos 90. Cos 90 is 0. Then T equals W over 2, 1 over 0. No? 1 over 0 is considered as infinity. Right? 1 over 0 is considered as infinity, which means T goes up to infinity now. T goes up to infinity. T increases up to infinity because it starts at W over 2 and it is going to end up at infinity. Then it should be an increasing trend, no? It should be an increasing trend, right? So both 1 and 5 are correct. In this particular year, right? In this particular year, this is a past paper question, no? This is a past paper question. In this particular year, since two graphs were given with the same shape, for both 1 and 5, marks were given for both 1 and 5. Otherwise, the shape should be either 1 or 5. Right? Shape should be either 1 or 5. Right? So take down if anything. And you can ask if any questions. Right? Let's move on. 10. The force F shows in the figure can be obtained by adding the forces F1 and F2 in. The force F shows in the figure can be obtained by adding the forces F1 and F2 in. Okay, this one. This force, no? Right. Then from this F1 and F2, easily you can argue using vector parallelogram law. Right? We know resultant of two vectors which are acting out from the same point is given by vector parallelogram. The diagonal which goes through vectors, no? Sorry. It is given by the diagonal which goes through vectors, no? This diagonal. So this is possible. This is possible because that diagonal is having the same shape as that, right? And these two in B, F1, F2 satisfies the vector triangle. These two in F1, F2 satisfies a vector triangle. Then if the forces are starting from here, F1 to F2, the resultant is given by the starting point to the end point, this. That is also correct, no? Same direction. Same direction. That is also correct. Right? For next one. Now, for this given diagram, you can't draw any parallelogram or triangle. Then in that case, what you can do is, you can redraw this as, see, you can redraw this as F1 acts upwards, F1 acts upwards, and F2 you can connect from here. Right? Now again the same diagram comes, see. So the resultant of these two is also like this. So it is also possible diagram. So all ABC are correct. That's an easy one if you know proper theories about vector parallelograms and vector triangles, vector parallelograms and vector triangles. Right? Okay, we are halfway through. Any questions so far? Anything to clarify? We are halfway through. 26 runs, you are now 27 weeks ahead of the exam, right? Just 27 weeks ahead of the exam, 27 weeks and 2 days, right? So it's a crucial time, a high time in your life these days, right? It's a life-changing period ongoing now. It's a life-changing period ongoing. 1 second. It's a life-changing period ongoing. It's calling. So even though the do not disturb mode is on, still the call is coming. Do not disturb is on actually. Right? Okay, let's see. All right, all right. Let's move on. Question 11. Question 11. A light string passing over a smooth pulley carries a spring balance of mass 1 kg and 2 weights, right? And 2 weights of masses 1 kg and 2 kg as shown in the figure. The reading on the balance will be, the reading on the balance will be, the reading on the balance will be, right? Again, reading of a spring balance is tension on hook, no? Reading of a spring balance is tension on hook, right? Reading of a spring balance is tension on hook. Then my target is finding tension on hook. And first check whether there are any accelerations here, right? Total unbalanced force acts in this direction is 20 newtons and total unbalanced force here in the other direction is also 20 newtons. Since these two are equal, right? Since they are equal, this is an equilibrium. Equilibrium. So no acceleration. A equals 0. Equilibrium. No acceleration. A equals 0. Right? That is an equilibrium. that is an equilibrium, no acceleration, A equals 0, right? No acceleration, A equals 0. Now, what's the question? The reading on the balance will be, right? Reading of the balance is tension on hook. Then mark these tensions. Let me use a different color. This tension is T, T, then here also T, 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 and T, right? To find it out, very easy. Consider this force frame. Consider this force frame. Write a vertical equilibrium. Very easy. Write a vertical equilibrium. Vertically upwards, there is only T for this force frame, Vertical downwards, there is only 10 newtons. That is only 10. So T equals 10 newtons, which means T equals 1 kg. T equals 1 kg. Very straightforward. Very much straightforward. Very much straightforward. Right? Very much straightforward. That's an easy one, no? That's an easy one for what we have discussed so far. Right? Write down if anything. Write down if anything. Okay, let's move on. 12. 12. See, it's kind of a different question for what we have discussed so far. Right? A different question for what we have discussed so far. Figure shows four coplanar forces A, B, C, and D drawn to the scale, acting on a point object O. Right? The resultant force are acting on O most likely to be acting in the direction. Okay. In these kind of cases, listen. In these kind of cases, if you need to find the direction of resultant, right? One of the most common approaches that we can use is you can dissolve these all forces in two perpendicular directions, simply horizontal and vertical. Right? You can dissolve these forces in two main perpendicular directions, vertical and horizontal. Right? Then let me draw a vertical line and a horizontal line here like this. A vertical line and a horizontal line. So this is a vertical line and this is a horizontal line. Now, if we think of the components which are coming to this, see, if we think of the components which are coming to this, look at the screen. One component from B is coming to this side, no? See, one component of B is coming to this side like this. One component of B is coming. And one component of B is also coming to this direction like this. The idea I am using is this. If you have a vector like this, right? See, you can dissolve this vector in these two directions. No? So these two will be equivalent to this size, vector for this size, and a vector for this size with the right angle triangle created here. Right? With the right angle triangle created here. This is how it is going to be. Right? If this is alpha, this component f cos alpha is equals to this size, and this side f sin alpha is equals to this height. Right? Let's use the same idea. See, then from this another vertical component is coming like this. From here also another vertical component is coming like this. Right? Now horizontally, look at here. First, let's conclude about the horizontal direction. Right? These two are added. These two distances are added. Once these two distances are added, See, once these two are added, right, this kind of a length is created, and this one is acting opposite. Then for sure we know the resultant of that is going to be rightwards, like this. The resultant of that is going to be rightwards. Resultant of that is going to be rightwards. For vertical direction, see what's happening. See what's happening with the vertical direction. What's happening with the vertical direction? Now, for this one, from this one, D, yeah, from D, a vertical component is coming. Let me use this. From D, a vertical component is coming this way, and a horizontal component is coming this way. Right? Right? Now, check these values of these two. Check these values. Now, if I add these two values, and if I compare it with this one, right? If you can't just observe it, what you can do is you can measure and see. Yeah. If you can't observe, you can measure and see. If you can't observe, measure and see. Right? Then this side is lengthier, no? Isn't it? This side is lengthier. Since that side is lengthier, which means resultant of the vertical direction is going to be downwards. No? Resultant of the vertical direction is going to be downwards. Simplify karan. Right? This one to this one. It is downwards. Then the resultant force of these two forces should be something in between, isn't it? It should be something in between. It should be something in between. So therefore, resultant of this diagram is going to be in this kind of a direction like 4. In this kind of a direction like 4. So basically what we are doing is dissolving the given forces in two perpendicular directions, vertical and horizontal, and compare them whether they are going to add or subtract in these given directions, right? If they act in opposite, get the subtraction, and subtraction if they act in to the same direction, get the addition, and find the final resultants. And final resultants are these two. So therefore, the resultant is going to be this, something in between. Resultant will be something in between, right? Let's move on. 13. An object of mass m is hung by using a string and is kept in equilibrium as shown in the diagram by a horizontal force. Force F, the magnitude of F is. Right, now to consider the equilibrium, do some construction like this with the vertical and horizontal lines. So if this is theta, we know this is theta now. Let's label this tension as T. Right, let's label the tension as T. Tension is T. Now what if you consider vertical equilibrium? Vertically upwards, we have T cos theta. And vertical downwards, that is mg, equation 1. And consider horizontal equilibrium. Horizontally leftwards, we have T sin theta. These components are T sin theta and T cos theta. No? Horizontally rightwards, F, equation 2. Right? Divide these two. That's it. 2 by 1. 2 by 1. Then T sin theta over T cos theta equals F over mg. Then T to T cancels. Sin over cos is tan. Tan theta equals F over mg. What we need is F. Right? So F equals mg tan theta. F equals mg tan theta. Equation answer 1. F equals mg tan theta. Answer 1. A simple equilibrium. Not a big deal. A simple equilibrium. Write it down. Not a big deal. A simple equilibrium. That's a simple equilibrium. Right? That's a simple equilibrium. Simple equilibrium. Right? Take it down. Take down if anything. And you can ask if any questions. Right? Okay, let's move on. 14. Two equal masses A and B are attached to a light inextensible string passing over a smooth light pulley. two equal masses, equal masses. As shown in the diagram, the mass B is moved down, held it stationary, and then released. Which of the following statements is correct about the subsequent motion of B? Right. Now, even though this is taken down, let's check the unbalanced force. Right? If their masses are equal, there's no unbalanced force in the system. This is also mg, this is also mg. There's no unbalanced force. If there's no unbalanced force, see, no unbalanced force, right? If there's no unbalanced force, which means this is an equilibrium, which means no acceleration, right? Simple as that. Then go to the statements given. We will move back. No, we won't move back because there's no unbalanced force. If there's a motion going on, there should be an unbalanced forces to proceed a motion. We will move back to the original position. No. We will stay stationary, correct. We will stay moved downwards, upwards. No. There's no motion at all. This is an equilibrium. There's no motion. Right? Even if to move a little distance, a small displacement even, there should be an unbalanced force. Right? Unless otherwise it won't move. Right? B is stationary. That's a good argument. Right? Next. 15. A weight W is hung on a tightly fixed rope as shown in the diagram. The tension in the rope is, okay, approximately W, okay. Now, to find the tension, let me do a construction here with a vertical line. And let's label these angles as theta. Theta and tensions as T, like this. Then vertical equilibrium. Consider vertical equilibrium. Vertical upward forces equals vertical downwards. Upwards we have 2t cos theta now. 2t cos theta equals W. Now question is about T. Subject T. So T equals W over 2 cos theta. Right. Now again, you should know this cos variation. I explained you before in the previous question as well. This is the cos variation. No? See, this is the basic cos variation. Cos theta with theta. Right? Cos theta with theta. Starts from +1, and when angle becomes 5/2, it comes to 0. Right? It is basically decreasing. Right. Now, the idea is like this. Look at here. Now, when it is starting, we know theta is 0. When theta is 0, cos 0 is 1. WO2 is coming. But here, now compare this angle. Consider this angle. This angle is close to 90 now, isn't it? This angle is close to 90. That is more towards an obtuse angle. Sorry, perpendicular angle. This angle is close to 90. This angle is close to 90. So close to 90 means, look at here, close to 90 means cos value is very less, no? See, close to 90 again, cos value is because it is going to reach 0 at 90. Now the angle is close to 90. Look, angle like now from the diagram you can see. Right? From the diagram you can see. That's a higher angle. So therefore, this value of cos theta is a lower value. Close to 0. When this denominator decreases, this increases. No, there is a higher value, greater value. This is very much lower. Means that is very much greater. When cos theta is very much lower, answer of T is very much greater. Right? Then approximately W, no. Next one, less than W2, no. In between, no. Much greater than W. That should be much greater than W. Because this is very close to 0. Right? Very close. This is very close to 0. ඒ කියන්නේ පොඩි value එකක් අක්කා. This is very close to 0. So when there is been a smaller value, this becomes a higher value. Right? Divided by a small value, no? It becomes a higher value. That's also a good argument. Right? That's also a good argument. Take down if anything. And raise if any questions. Right? Raise if any questions. Raise if any questions. Right? Raise if any questions. Right? Let's move on. 16. Moving on to the last 5 questions for the day. 16. A uniform bar of mass m suspended from its midpoint by a spring balance. Two masses m1 and m2, m1 greater than m2, are placed at the two ends of a bar. A wedge supports the bar at the end of B, to keep horizontally as shown in the figure. The reading of the spring balance is, okay, again, you know, reading of a spring balance is tension on hook. Now my goal is finding T. Simple as that. So this is T. Right? It's a uniform bar. Suspended from the midpoint. Then weight also acts from here, capital MG. And here also there's another weight acts by M1G. Right? On the bar, M1G mark without marking other reactions. Right? On the bar, that is M1G. Right? That's all. No? That's all. Now we can consider force moments about B considering the equilibrium. Right? Force moments about B considering the equilibrium. Right? Considering equilibrium. Right? Force moments about B. Then leftward force moment is due to mg, capital Mg, perpendicular distance. Let's consider these lengths as L and L. So perpendicular distance is L. Right? Plus M1G also rotates in the anticlockwise direction. Distance from B is 2L. Right? Right hand. Now fine, right? Now it's fine, right? There. Okay, right. Let's move on. 17. A bird of mass m sits on a tightly stretched telegraph wire as shown in the figure. The additional tension produced by the bird in the wire is, right? Additional tension produced by bird on the wire is, right? Now again, this question is very much similar to, compare these questions, very much similar to question 15. This question is very much similar to question 15. Now here also, I will draw a vertical line like this. We'll draw a vertical line like this and going to mark these angles as theta. And let's assume this tension as T and weight of this bird as W. See, same thing, very much similar questions, very much similar questions. Vertical equilibrium. Consider vertical equilibrium. Consider vertical equilibrium. Then vertically upwards, we have 2t cos theta. Vertical downwards, W. Vertical downwards, W. Right? Then about T, they are asking, no, the additional tension. Okay. Subject T. T is W over 2 cos theta. Right. Same argument like before. Right. This is a cos variation. Right. This is a cos variation. Right. Cos 90 is 0. Cos 0 is 1. Right. Then for large angles close to 90. Right. This is my argument again. For angles close to 90. For angles close to 90, right? This value is a small value, right? This value is cos theta is very small. Cos theta is very small because it is reaching 0 at 90, right? This is an angle close to 90. Argument, that's the argument. This is an angle close to 90. So therefore, this value of cos theta is very small. When this value of cos theta is very small, right, this theta is very large. This t is very large. When the value of cos theta is very small, t is very large. Right? T is very large, then more than mg, less than, more than mg. That is actually very much than mg, very much than mg. Right? More than mg. Right? Very comparative with question 15. Very comparative with question 15. Very comparative with question 15. Right? Take down. So it clearly shows that this angle is, right, when you mark the angles, it clearly shows that angle is close to 90. Yeah? It's an angle close to 90. Right? Mathematical arguments. Otherwise, you can't just think here and finalize the answer. Right? You can't just think and finalize. That's a mathematical answer. Right? I approach the answer mathematically. Right? You can't just merely think about the scenario given. Always get a mathematical backup. Right? Equations never lie. Get a mathematical backup. Then for sure, I know when this equation says it is like this, t equals W02 cos theta, then it is a solid argument. Correct in the sense that is a solid argument. That's a solid argument. Right? 18. Three masses ABC are hanging from horizontal crossbars as shown in the figure. Each crossbar has negligible masses. If A has a mass 6 kg, okay, if this is 6 kg, this weight is 6g, no? Right? 6g. Weight is 6g. The masses B and C respectively are. Okay. Now, if this tension is, look at here, if this tension is, let's say, T1 here, if this tension is T1 here, T1, right? Considering force moments about this point, let's say A, about point A, we can find T1. Considering equilibrium, right? Force moments about A. Counterclockwise force moment is due to 6g. Then that is 6g into x. Anticlockwise force moment is due to T1. Distance is 3x. T1 distance is 3x. X to x cancels. Right? Sorry, this is 3 times 2. Then it says T1 equals 2g. T1 equals 2g. So 1 is coming. This says 2g. 2g means the mass is 2 kilograms. Right? That is 2g. Right. Then if these two weights are, let's say, if these two weights are, let's say, MB and MC, right? One thing that you can say, considering this equilibrium is, at answer if you can directly see the answer this point onwards, right? If you can directly see the answer this point onwards, you can pick it at once. Right? I'm explaining further to all of you to understand. Otherwise, if possible, you can pick this answer at once. Now, considering this vertical equilibrium of this system, T1 equals MBG plus MCG, no? Then T1 is 2G. 2G equals MBG plus MCG. G cancel. 2 equals MB plus MC. See, 1 is coming like this. Then the addition should be 2. Addition should be 2. So this is strong. Addition should be 2, no? Others are possible. Right? For now, other values are possible. Now then, to finalize it, if you didn't see the final answer, finalize it. Write another force moment about this point B. See, if you write a force moment again about point B, it is coming. About B, MBG rotates in this direction, then MBG, right, times Y, opposite direction, MCG times 3Y. Then Y cancels, G cancels. See, it says MB equals 3MC. That's done. Then for MB, you can plug something from here, no? For MB or MC, that's fine. For MB, from here, MB equals 2 minus MC. See, then MB is 2 minus MC equals 3MC. Take it to the other side. Let me move it a little bit. Okay, see, visible, right? Okay, see, then 2 equals 4 MC. MC equals half, 0.5 kg. MC equals half. If MC equals half, MB. If MC equals half, MB equals 2 minus half, 1.5. Right? Then 1.5 and B and C, 1.5 and 0.5. 1.5 and 0.5 answer to. Another simple calculation from equilibrium. Right? Take down and ask questions if anything. Right? Take down and ask questions if anything. Equilibrium, a simple question from equilibrium. Fine, I wrote force moments about A and B. Okay, let's move on. 19. Figure shows an attempt made by a man to hold a bull tied to a rope, trying to escape. The force exacting on the bull's leg is FL. Let me mark those forces. Then on bull's leg, it is FL, no? It is given as FL, right? Then how this FL comes is like this. We know perpendicular reaction is vertically upwards, no? Look at here, this is a kind of good one. Perpendicular reaction is vertically upwards, like this. And when this bull is trying to, bull's leg in the sense bull's foot is trying to move towards this direction because of this tension of the string. When it tries to move towards this direction, what is happening is friction will be opposite. So therefore, friction here acts in this direction. Friction acts in this direction, right? So therefore, resultant of these two is going to be something in between like this. Resultant of these two is going to be something in between like this. And that is what is given as, right, force act on the bull's leg, FL. Then this should be our FL. This should be our FL. Force act on leg. There are two forces acting. Then consider the resultant. This is FL. This should be FL. Got it? Then, and that on the ground is FG. According to Newton's third law, if force act on the foot of the bull is FL, equal and opposite force acts, mutual forces, no? Equal and opposite force acts on ground. Then equal and opposite of this should be acting on ground like this. Equal and opposite of F is FG should be acting like this, right? Because these two follows Newton's third law. These two follows Newton's third law, right? That's done. Then the force at Y acting on the rope is FR. Acting on the rope is FR. Now, if I mark these tensions, right, this tension is on hand. This tension is on hand. And equal and opposite tension of this is on rope. This tension is on hand and equal and opposite will be on rope. Then the force at Y acting on the rope is FR. Then if there is on the rope, it should be in the leftward direction like this. Then this should be our FR. No? This should be our FR, leftwards. And hand, that on the hand of the man is FH. Then this should be our FH. This should be our FH. Right? Basics of Newton's laws, FH. Right. Then we can identify. FR should be rightwards. Right? FL and FG are like this. Then what is remaining? 1 is there, 2 is there, and check R. FR is rightwards, FH is leftwards. 2, right? Answer 2. Identify these forces. Identify these forces. Force identification, right? So in Newton's laws also we usually discuss, right? Force identification, equilibrium, vectors. So everything is connected. No? Everything is connected. Everything is connected. So these pairs follow Newton's third law, Fg and Fl, and this Fr and Fh. They follow Newton's third law separately. They follow Newton's third law separately. Right? Alright. 20. Figure 1 shows a book A placed on top of a box B, right, which rests on the floor. Figure B shows the free body diagram, free force diagram for the box P, Q, and R indicate the forces acting on the box. Which of the following statements is true? Which of the following statements is true? Right. Now, all forces acting on this one is given. No. If I mark the forces here, see, if I mark the forces here, there should be one force acting on this one from the ground, let's say R1, and weight of this box should be acting from its center of gravity like this, mg, and weight of this box also should be acting from its center of gravity like this, and there should be a reaction on A by the box as this, say R2, and equal and opposite reaction on this should be on the box again, downwards. Let me mark it somewhere here, right? R2, like this. These are the forces acting now. Now we can easily identify these given forces. They are given as PQR, doesn't matter. You should be able to identify. You should be able to identify. These are given as PQR. Now identify them. Identify them. Now let me mark forces belongs to A in yellow. See, belongs to A in yellow. This belongs to A. This mg belongs to A, right? Then these are belongs to B. Green ones belongs to B. This one belongs to B. This one belongs to B. This one belongs to B. Right. Now let's see. Q greater than P plus R. Consider vertical equilibrium. Consider vertical equilibrium of this. Vertical equilibrium. Vertically upward forces equals vertically downwards. Vertically upwards, how many forces we have? Only one, Q, equals downwards P plus R. Then Q equals P plus R, not Q greater than P plus R, that is wrong. Q equals P plus R. Q equals P plus R. Right. Second one, force on the flow exerted by the box is indicated by P. Force on the flow exerted by the box. No. What is P? What should be P? Compare this with our diagram now. P should be the weight of this one. This is the only downward force acting on. This is the only downward force acting on. Sorry. This is the only downward force acting from the middle of B. No? Acting from the middle point of B is mg. No? So P should be force on the flow exerted by the no. P should be mg. So that is wrong. P should be mg. P should be mg. That is how you should identify these forces. P should be mg. 3. Force on the flow exerted by the box is indicated by Q. Force on the flow. No. Q is not a force on the flow. That is on the box. Q is on the box. This is on the box. Wrong. Not on the floor. That should be on the box. 4. Force exerted on the box by the book is indicated by R. On the box by the book. R. R. In my case, that is R2. This is correct. This is correct. On the box by the book. Right? Now, this R is R2 in my case. On the box by the book. On the box by the book. That is correct. This is also wrong. So, answer is 4. Answer is 4. That's a good one. A good argument. A good argument. Forces are not given namely. Forces are not given namely. Right? Forces are not given namely. Right? You have to identify them. You have to identify them. That's the thing. They are not given namely. I have to identify. Right. All right. So with that, we have come to the end of the 20 MCQs we discussed from vectors and force equilibrium. Right. See now, sometimes what you are knowing from theories, right? What you are knowing from theories are used in a different manner here in a question. So that is a skill you have to practice. Huh? That is a skill you have to practice. Sometimes you might be knowing all the theories about equilibrium, right? You might be knowing all the theories about equilibrium, but yet you can't tackle questions. You can't try. You can't do actually. You can't do questions. You can't tackle questions. The reason is practice is not enough. Practice is not enough, right? So that's the main purpose behind these S2A discussions, to make you comfortable and like familiar and comfortable with these questions. Even though some students know all the theories, 100% theories are known, but yet they can't do even a simple question, right? The lack of practice. Good up practice come down. That's the thing. So once you get this experience, now if you get a same type of a question again, right? If you get a same type of a question again, right? Give me 1 second. Right. If you get a same type of a question again, now it won't be forgotten. I mean, with the experience, you will tackle somehow. That's the thing. Right? You will tackle somehow with the experience you got. You will tackle somehow with the experience you got. Right? You will tackle somehow with the experience you got. So likewise, final target is facing the exam. So by the time you face the exam, right, higher the experience you got, right, higher the experience you gathered, right, more likely to do the question in the exam. Right? That's the idea. It's more likely to do the question in the exam. මේ හැම question එකම experience එක ගන්නයි ඕනේ. Right? Knowing all these question types, you have to know these question types. Right? Exam එකට ගිහිල්ලා for the first time don't don't imagining of having a question for the first time in your life. I mean, a whole new question. No, you should get the experience. Right? Modifications තියෙන්න පුළුවන්. For sure there will be modifications, right? For sure there are modifications, right? But it should be something modified from a known type of a question. That's the idea. It should be something modified from a known type of a question. So since there is a known type, you can tackle the question easily with your past experience you have. With the past experience you have. That's the whole idea here. Right? Okay. That's the whole idea here. So that was the main purpose behind these S2A discussions. Right? All right then. So, any questions? about the 20 questions we discussed so far today. So far in the sense about the 20 questions we discussed. Or is it clear enough? If any questions you can ask, or any other thing even about the subject, studies, classes, or any other thing even. If there's anything you can ask. Now we finished the session like 8 minutes before than the usual time. No? Any questions? No. Right. So if no questions, I will wind up. Right. If no questions, we will wind up. You are 27 weeks ahead of the exam. So don't waste the time. Don't waste the time. This is the most critical and the crucial time period you have in your lifetime. Right? It decides where you are going to go and where you are going to be in next 5 years. Right? It is going to determine where you are going to be in next 5 years, where you are going to be in next 10 years. Right? So it's critical. It is going to change your whole life. Okay then we'll wind up. Study hard and let's see you again with another S2 discussion. Right? Good night and goodbye.